Maybe the universe is not out there. Maybe it's inside us. Maybe consciousness itself is the bridge between stars and thought.
In this silent darkness, reality folds into itself. And yet, nothing is ever truly lost.
Perhaps the universe never forgets. It only hides its memories in the threads of reality.
Every story burned by the universe is rewritten in the language of light.
If the Big Bang was the inside of a black hole from another cosmos.
Hello to the wonderful Deep Dive family. I'm so happy we're gathered here together again. Imagine writing down your life's most important secret, the very thing that defines your identity, on a piece of paper. Then, you throw that paper into a furnace and watch as it burns, turns to ash, and vanishes forever. Now, imagine our entire universe is a colossal library, and black holes are the furnaces that incinerate its books, the stories of stars, planets, and perhaps even ourselves, destroying them for all time. This idea is the most terrifying thought in all of physics, but by the end of this video, you'll discover that maybe, just maybe, there's a way to read those cosmic ashes. But before we get there, we have to start at a cosmic crime scene. We live in a universe built on two main pillars, two laws that, like two legendary detectives, are each flawless and beautiful on their own. The first pillar is Albert Einstein's theory of general relativity. This law tells the story of the big world, the story of gravity, the curvature of space-time, the dance of galaxies. It's an epic poem about the colossal scale. The second pillar is quantum mechanics. This law tells the story of the very, very small world, the world of subatomic particles, strange probabilities, and a reality that, until you look at it, seems undecided about what it wants to be. It's a mysterious, magical story. For decades, these two great detectives, relativity and quantum, worked in separate precincts, never having a serious confrontation. But one day, a cosmic criminal appeared that forced them into the same interrogation room. That criminal was the black hole. And the question placed on the interrogation table was simple, yet shattering. When something, anything, crosses the point of no return of a black hole, what is the fate of its information? Can the story of our universe be erased? Let's imagine a black hole as a cosmic waterfall, a massive cascade pulling the stream of space-time toward a single point. The closer you get, the stronger the current. At a certain point, the flow becomes so powerful that even if you could swim at the speed of light, there's no way back. This point of no return is called the event horizon. Einstein tells us that anything crossing this horizon is forever cut off from our universe. Its information, its structure, its story, all of it is imprisoned on the other side. It's as if a book from the cosmic library has been taken and locked in an ultra-secure safe whose key has been lost forever. So far, you might say, well, the information isn't gone, it's just imprisoned. What's the problem? The problem began when a young, infinitely brilliant physicist named Stephen Hawking entered the scene. By combining the laws of quantum mechanics with the physics of black holes, Hawking made a shocking discovery. He realized that black holes aren't completely black. Due to a strange quantum effect at the edge of the event horizon, they emit a very faint, imperceptible glow known as Hawking radiation. This radiation causes the black hole to lose mass over time, very, very slowly, and shrink. Over an unimaginably long period, the black hole completely evaporates and disappears. Wait a minute, what does that mean? It means the safe that was holding our book is itself going to be destroyed. So what happens to the book? In his initial calculations, Hawking reached a terrifying conclusion. Hawking radiation is completely random and thermal. It's like the steam rising from a kettle. By analyzing that steam, you can't tell if the kettle held water, tea, or coffee. It contains no information about its original contents. So, when the black hole fully evaporates, that book, that information, that secret, is forever, truly, and absolutely erased from the universe. And this is where the alarm bells go off in the world of physics. Because one of the most sacred laws of quantum mechanics, a principle called the conservation of information, or unitarity, states, information is never, under any circumstances, destroyed. It only changes form. Just as energy is not destroyed but only converted from one state to another, the same is true for information. When you burn a book, in theory, if you could track every single molecule of smoke, ash, and heat, you could reconstruct that book. The information is just scrambled, not destroyed. But the black holes seem to be a cosmic deletion machine, a delete button for reality. This conflict between Einstein's claim that information is trapped behind the event horizon, Hawking's claim that the prison will be destroyed, and quantum's claim that information can never be destroyed, is called the black hole information paradox. It is the greatest crisis in modern physics. It was as if our two great detectives, Einstein and quantum, had reached completely contradictory conclusions on the same case, and the credibility of the entire judicial system of science was in question. Physicists couldn't accept this catastrophe. For decades, the best minds in the world tried to find an escape route for information. These efforts led them down two main paths. The first path was, maybe we've been accusing the wrong culprit all along. Maybe what we call a black hole isn't really what we think it is. This idea gave birth to a whole zoo of strange and exotic cosmic creatures called exotic compact objects. These are objects that, from a distance, look exactly like black holes but have one crucial difference. They have no event horizon. One of these theoretical creatures is called a gravastar. Imagine a gravastar as a cosmic egg. Its shell is made of ordinary matter, but inside, instead of a yolk, there's a massive core of dark energy exerting negative pressure, preventing a total collapse. Since it has no event horizon, information is never truly imprisoned. It's like it has a glass wall, not a one-way mirror. Another idea emerged from string theory, called the fuzzball. This model suggests a black hole isn't an infinitely dense singularity at the center, but rather a giant, tangled ball of energy strings at the scale of the horizon itself. When something falls in, its information gets encoded like a pattern onto the surface of this fuzzball and is never lost. These ideas were clever, but they had a major problem. How could we ever know if that dark, giant object at the center of our galaxy is a classic black hole, a gravastar, or a fuzzball? The answer came from an unexpected place, from listening to the sound of spacetime. With gravitational wave observatories like LIGO, we can listen to the vibrations in spacetime created by the collision of two black holes. When two black holes merge, the new object quivers for a few moments, like a ringing bell, producing specific gravitational waves. Theory predicts that if the new object is a classic black hole with an event horizon, the horizon acts as a perfect absorber, and the vibrations fade away quickly. But if it's a gravastar without a horizon, its surface would act like a mirror, trapping some of the gravitational waves between the object's surface and a gravitational barrier around it, producing something like echoes. To this day, we've listened to dozens of collisions, and in not a single one have we found an echo. It seems the prime suspect is, in fact, Einstein's classic black hole. So, we were back at square one. But wait, why should any of this matter to us? Why should we care about the fate of information falling into a black hole millions of light years away? Because this isn't just a complex physics debate. This is a question that strikes at the heart of our identity, at the meaning of our existence. Does our story, our memories, our love, all the information that makes us us, ultimately end in nothing? Is the universe forgetful? This paradox isn't just a cosmic puzzle. It's a profoundly human question. And that brings us to the second path of investigation. A path that has sparked a revolution in recent years. Maybe the culprit is the black hole, but we've been looking at the crime scene from the wrong angle all along. What if the black hole isn't an information murderer, but a masterful magician? What if it doesn't destroy the information, but pulls it out of its hat in a way we never thought possible? This is where we encounter one of the strangest and most beautiful concepts in physics, quantum entanglement. Entanglement means two particles can be magically linked, their fates intertwined, even if they are billions of light years apart. If you measure one, you instantly know the state of the other. Einstein called this spooky action at a distance. Now, let's apply this idea to a black hole. The new theory suggests that when a particle of Hawking radiation escapes the black hole, it is entangled with another particle that remains inside. Early in the black hole's life, these escaping particles are entangled with particles inside. But as time goes on, when the black hole reaches its half-life and begins to shrink, something amazing happens. The newly escaping radiation particles start to become entangled with the radiation particles that had already escaped. And this is the turning point of our story. This means that the information about the things that fell into the black hole is, in an encrypted form, hidden in the pattern of entanglement among all the Hawking radiation particles that have been emitted from the black hole over billions of years. The information hasn't been destroyed, it's just been translated into a highly complex quantum language and encoded within that seemingly random radiation. This idea led to the concept of entanglement islands. It's as if, inside the black hole, there are islands of information that are quantum mechanically connected to the outside world. The black hole isn't a safe that eventually gets destroyed. It's a highly advanced cosmic shredder. It takes the book, reduces it to the smallest possible particles, and then emits those particles in an encrypted form through the factory's smokestack. It's incredibly difficult, but in theory, if you could collect all of that smoke and had the decryption key, you could reconstruct the original book. This was a revolution. It means that the quantum law of information conservation wins, even against the most violent and bizarre phenomenon in the universe. It means the universe is not forgetful. The universe never forgets a single story, no matter how small. Remember at the beginning of the video when we talked about that burned secret, that book thrown into the cosmic furnace? We now know that no fire, not even the fire of a black hole, can truly destroy a story. It just tells it in another language. A language of probabilities, entanglement, and quantum physics. This gives us a profound sense of hope that maybe nothing, no memory, no experience is ever truly lost. Perhaps they are all preserved forever in a vast cosmic memory in a way we don't yet understand. As the great astronomer Carl Sagan once said, "We are a way for the cosmos to know itself." Perhaps black holes are a way for the cosmos to remind us that no story ever truly comes to an end. Thank you so much for joining me on this deep journey to the very end. Being here with you, exploring these great mysteries, is the greatest honor for us at Deep Dive. We're not a team, we're a family of curious minds, and you are the heart of this family. We love you guys so much. Now I ask you, if you could ask a black hole one question, what would you ask? Write your answers in the comments. I can't wait to read them. And if you enjoyed this video, please help our family grow by liking and sharing it. Perhaps the next time you look up at the night sky, you'll remember that absolute darkness is not an end, but an infinite memory.